How do FPSOs work? Offshore oil production explained. Floating production storage and offloading installations are a cornerstone of modern offshore oil and gas production. These vessels act as integrated platforms, handling extraction, processing, and storage before transferring hydrocarbons to shuttle tankers or pipelines. Designed for deepwater and ultra-deepwater environments, FPSOs operate where fixed infrastructure is not viable. As a result, they have become essential to global offshore development, with more than 270 units currently in operation. This capability enables efficient production. By combining multiple functions into a single floating system, FPSOs support continuous operations in challenging conditions. Understanding their structure and production processes is key to explaining their effectiveness in modern offshore energy systems. The evolution of FPSO technology reflects major advances in offshore capability. Early developments began with Shell's Castellon, installed in water depths of around 117 meters. Since then, continuous innovation has pushed operations into much deeper environments, with installations now reaching depths of up to 2,900 meters. As a result, capacity has expanded alongside depth. Modern FPSOs can process more than 250,000 barrels of oil equivalent per day, compared to around 30,000 in earlier designs. Storage capacity has also increased significantly, from about 11,000 barrels to as much as 2.3 million barrels in large-scale units. This progress is matched by rising investment levels. Capital costs now range from roughly $200 million to over $3 billion, depending on vessel size and project complexity. Overall, the development of FPSO systems shows how the industry has scaled technology to meet growing offshore production demands. Crude oil production on an FPSO begins with hydrocarbons extracted from subsea reservoirs through wells connected by risers and flow lines. These systems transport a mixture of oil, gas, and water from the seabed to the vessel for processing. Once on board, the flow enters separation systems that divide it into crude oil, natural gas, and produced water. The oil is stabilized and stored in tanks within the hull, while gas is treated separately, used as fuel, re-injected, flared, or exported depending on the system design. This process also includes water and impurity management. Produced water is treated to meet environmental standards before re-injection or safe discharge, while solids and chemical residues are handled under strict controls. After processing, storage and export complete the cycle. When capacity is reached, crude oil is offloaded to shuttle tankers for transport to onshore refineries, while gas may be exported via pipelines or as LNG where infrastructure exists. As a result, FPSO operations rely on integrated control systems. Continuous monitoring ensures stable production, while safety and environmental measures help minimize risk and support responsible offshore operations. The design of an FPSO is structured to ensure efficient, safe, and continuous offshore production. The vessel is divided into three core components: the topsides, the hull, and marine systems, each contributing to overall functionality. The topsides form the operational center of an FPSO. Located on the deck, they house processing equipment for separating oil, gas, and water, along with systems for gas compression, water treatment, and power generation. Safety systems, including flaring, manage excess gas, while control rooms and living quarters support both operations and crew welfare. This structure connects directly to the role of the hull. The hull provides buoyancy and serves as the main storage area, capable of holding millions of barrels of treated oil. Ballast systems regulate stability by adjusting seawater levels, while mooring systems, typically turret-based, allow the vessel to rotate with wind and waves, reducing structural stress. Marine systems complete the vessel's functionality. Navigation tools, communication systems, and offloading equipment enable coordination with external vessels and the transfer of oil to shuttle tankers for export. As a result, FPSO design must balance performance with resilience. Harsh offshore conditions, limited space, and strict safety and environmental requirements demand robust materials and advanced engineering, supported by continuous monitoring, regular maintenance, and efficient layout planning. Advances in FPSO technology have significantly improved performance, efficiency, and sustainability, addressing long-standing operational challenges. One of the key developments is modular construction, where components are built and tested onshore before installation, reducing costs, shortening timelines, and simplifying maintenance through easier upgrades and replacements. This progress supports digital transformation. Advanced sensors and real-time monitoring systems provide continuous oversight, enabling early detection of issues. Predictive maintenance reduces downtime, while automation limits manual intervention and enhances safety. Environmental innovation is also becoming more central. The use of renewable energy support systems, such as solar and wind, helps reduce fuel consumption, while technologies like waste heat recovery and carbon capture lower emissions. Subsea processing further improves efficiency by separating oil, gas, and water on the seabed before reaching the vessel, reducing the processing load on the FPSO. As a result, FPSO technology continues to evolve toward more efficient, resilient, and sustainable offshore operations. FPSOs represent a peak in offshore engineering, combining advanced technology with efficient design to enable oil and gas production in some of the most challenging environments. From subsea extraction to offloading, their processes are highly optimized, with integrated layouts allowing multiple systems to operate within a compact and dynamic structure. This capability supports sustained operational efficiency by combining processing, storage, and export in a single unit. FPSOs enable continuous production in deep water and remote locations. Ongoing innovation remains essential. Advances in technology continue to improve performance, safety, and environmental management, allowing FPSOs to adapt to evolving industry demands. As a result, FPSOs remain central to offshore energy production, playing a key role in meeting global demand while supporting more efficient and sustainable operations.